Okay, what we need to talk about here a little bit today is some new ways of evaluating limits besides relying upon a table, more directly evaluating limits is what specifically we're going to try to cover a little bit here in the next few moments. Okay, so I've given you that handout there, and so what that handout is helpful for is not that you necessarily have to know those limit laws, but I did want to kind of touch on them and give you some background of why these evaluation techniques work. There are some laws behind it. You don't have to memorize these laws, but on the handout there, just looking at some limit laws. On number 1, we see that the limit as x approaches a, I'm not going to write them all down, but start with a few of them. F of x plus g of x equals the limit as x approaches a of f of x plus the limit as x approaches a g of x. Yeah. They're kind of tedious to write out, but the good news is they're very nice. These limit laws are very nice in application, because what this is telling me is that if I've got a function, well, it's a function comprised of functions. So I've got two functions added together to make another function. If that's the case, then all I have to do to evaluate that is just evaluate them separately. Basically, do the f of x limit, and then also limit, do the limit of the g of x. So you're kind of doing those separately, and then number 2, well, number 2 is very much the same as number 1, except what? You got minus instead of plus, so the same thing works. So number 2, without writing it all again, but number 2 is just same thing with subtraction. Number 3 is somewhat different, so let me mention it. Yeah, it turns out on limits, so we're going to x approaching a. Well, this, and not just for limits, but in general, in a rule of thumb for, in most math books, is that a c, x is the variable, but the letter c, that designates a constant. So it's just a number. So I've got a number times some function of x. Well, by limit law number 3, you can just bring that c out, because the limit is x approaches a. So there's no x part in that. X is approaching a, so that's not going to affect this number. It's just a constant, you see. So you can bring it out of the limit. So, like I said, these are very nice. We're just moving that out. Number 4 and 5, those are the analogous ones to 1 and 2, except what do we got in 4 and 5? Multiplication, and number 5 is division. So you can do the same thing on limits with multiplication and division. Now, I would point out that these 4 and 5 limit laws, those are very special, that you can do those with multiplication and division, because we're going to learn some other rules that you can't do it with. You can do it with addition and subtraction, like number 1 and 2, but you can't do it with multiplication and division. So limit laws, like I said, are very nice in that basically you can break down whatever it is, whether it be addition, subtraction, multiplication, division, constant in the front, you can bring it out. Very nice. Okay, so, and then number 6 has got the power, f of x to the nth power, so we can bring out the power, do the power outside. Now, 7, 8, and 9, those are kind of where we get to the nitty-gritty of the actual evaluation. Yeah, you can say that the limit as x approaches a of a constant Well, like we just said, that's a constant, so as x approaches a, that number's not going anywhere, so that's just a constant. Limit as x approaches x. So limit as x number 8 is limit as x approaches a of x. Well, that's just x. And then number 9, the limit as x approaches a of x to the nth. That's going to be a to the n. All right, so these are kind of getting to where we actually do some evaluating of limits, because this is saying this limit is a to the n. Now, notice what specifically 8 and 9. Oops, number 8 is that. Sorry. Number 8 is limit as x approaches a of x equals a. Limit as x approaches a of x to the n is a to the n. But number 8 and 9. That's kind of where we're going with this. Do you see actually what I've done here to get this limit? Let's look at number 9 specifically. How did I get a to the n from x to the n? What did I do? What did I substitute in? Didn't I substitute a for x? That's what I did. Well, x was going to a, and so yeah, I just substituted in a for the x. That's in limits. That's what you're looking for is to get it to where I can substitute whatever x is going to. I can substitute that in. That's our whole goal in evaluating the limits. If I can get it to that, then I'm in business. These other laws can get us there. As a matter of fact, 10 and 11 say, well, 10 is similar. You just plug in. We're just plugging in the a for the x. That's just saying if I've got it work. This for the nth power, x to the nth power. This is for x to the nth root. Well, same thing. I just plug in a for x. So, moral of this story is, there's number 11, but moral of the story is, yeah, that's what I want to be able to do. I want to be able to just substitute these in. Well, these limit laws give me a nice way, very nice way of doing that. There's just, usually what happens is we have to get to some work where I can do that. So here's what I want to do with these. I'm just going to do this one time just so, and I think on the homework there's just one problem, maybe two, but where you have to specifically tell the limit laws, just so you're aware, I'm aware that you're aware of these laws. Here's what I want to say. All right, so let's say I've got the limit as x approaches 3 of x squared minus 3x plus 4. Let's evaluate this limit and justify each step. And the way we're going to do that is just indicate which limit law we're using. Like I said, we're only going to do this once in class and then maybe once on your homework, okay? So you don't have to memorize these limit laws, just be aware. Okay, so if I'm going to use these laws for this problem, the first thing I can do, right, is by number 1 and 2, what can I do? Well, don't you see I've got subtraction and addition, so by limit law 1 and 2, I can split that up into individual limits. I can do this into the limit as x approaches 3 of the x squared minus the limit as x approaches 3 of 3x plus the limit as x approaches 3 of 4. So I'm just individually going to evaluate those limits. So that's limit law, and I'll just say that's limit law 1 and 2. With me there? That's what allows me to do that. Limit law is 1 and 2. Because I'm just breaking up the subtraction and the addition. Okay, you tell me now. What can I do next? What can I do with this one what limit law can I apply to that one? I'll just do them individually. Based on the handout there. Limit law number 8. Actually, limit law number 9, isn't it?
Yeah.
Because we've got x to a power. So that's an application now of, I've got x to the second power. N is some power. So what can I say for that one by limit law 9 here? That's going to be a squared. What's the a? A is what the x is going to. So isn't by limit law 9 this 3 squared? 3 squared. Now, we can't do the same thing for that middle one because we don't have one that says limit law of something times x. But we'll just have to go a couple of steps here. What can I do with or the middle part? Well, I guess there's a couple of things I can do. I can do limit law 3 on that one, can I? Because I've got a constant in front of an x, and so I can bring that out, so that becomes minus 3 times the limit as x approaches 3. Now x, that's my limit law 3. And then what about that one on the end? What can I do with that? What limit law applies there? Number 7? Yeah, I've got the limit of a constant. In this case, the constant's 4. So the limit of a constant is just the constant. So that's 4. Is that okay? That's, what was that? Limit law 7. Limit law 7. So that's what they're wanting us to do. Just apply each of these laws that we need to. Okay, now, that leaves us the middle one, but the middle one now by limit law 8. Limit law 8, I can say, so we got 3 squared. Let's leave it that way. I'll evaluate here in a second. So 3 squared, bring it down 3 times by limit law 8. As x approaches 3, that goes to 3, and then plus 4. So on that problem in the homework, that's sort of what they have in mind there. You won't have to do this for one problem. So anyway, we get 9 minus 9 plus 4, so we get the limit here. This limit is 4. Now, hopefully, see what we did there. Good news is, all we really have to note is this. What did I actually do? Look at this step right here. To evaluate this limit, what did I actually do? 3 squared minus 3 times 3. I just plugged in the numbers, right? I plugged in what the x value was going to. That's the good news to this. And it's because of all these limit laws. But because of all these limit laws, when I get a limit down to where I can just substitute whatever the x value goes to, when I can just substitute that in, that's how I'm going to do it. So for example, if I have the limit as x approaches 2 of x minus 6 over x plus 3. This is going to be a very easy limit. I don't have to go to a table. I don't have to do anything besides, right now, is just substitute that in. That's what the limit laws tell me to do. If I can substitute the x value 2 in and evaluate that limit, that's the way I'm going to evaluate that limit. So this limit's going to be 2 minus 6 over 2 plus 3. It's negative 4 over 5. It's going to be that easy. Okay. So this is good news. Now, the little bit of bad news that comes with that is we're going to run into ones like this. Say I have the limit as x approaches 2 of x minus 2 over x squared minus 4. Okay, so the problem with this one is, using the limit laws, is if I plugged in the 2, what do I get? Zero, but over 0. Uh-oh. I can't do that because why? 0 divided by 0 is not a number. Why? You can't divide by 0. You have a denominator of 0. So that's one reason. Usually what they refer to this form is, they refer to this form of this limit as the form 0 over 0. Whenever you have the form of a limit is 0 over 0, meaning if you substitute in what x goes to and you get 0 over 0, that's what's known as an indeterminate form. And so that means you can't substitute x to be whatever that x value is in. You just can't do it that way. However, that's what we're going to talk about in the next few moments is what can we do if we have, so 0 over 0, that's indeterminate. An indeterminate form. In our sequence of courses, we talk a lot more about indeterminate forms in Calculus 2, but just FYI, if you get 0 over 0, that's an indeterminate form because, like we said, you can't divide by 0, and so that's just indeterminate. What happened, the reason it's called indeterminate is because what can happen when you have 0 over 0 is you can get 0 over 0, that can actually turn out to be a number. 0 over 0, it could turn out to be infinity, negative infinity. There's actually, it does not exist, that could happen. So there's a lot of things that could happen when you have 0 over 0, and so that's why it's called indeterminate. Just say, I don't know what happens right now. Let me look at some other things, and that's what we're going to look at. Turns out one technique, that's the technique we're going to use here, that we can use on this, is factoring. Let's just go right here, okay. We're going to use some factoring. All right, so let me rewrite it. Limit as x approaches 2, x minus 2 over x squared minus 4. Yeah, if you plug it in and you say, oh, I've got the 0, 0, one thing you can always look for is the factor. And in this case, it's the denominator that factors, right? X squared minus 4, I can factor that as a difference of squares. X squared minus 4 factors as x minus 2, x plus 2. Okay. Now here's where nice things happen, or a lot of times nice things happen when we get this factoring. We notice there, what have we got? We've got a common factor, don't we? X minus 2, we have a common factor. Well, you know, a lot of times you have to say, well, if I cancel that out, I have to note that I canceled it out. Here we don't, because x minus 2, the kind of the point of concern there is actually x is 2. It eliminates one of the undefined parts of this expression, taking that out, but it's where x equals 2. And in limits, if you think back on tables, we don't really care on limits what actually happens at x equals 2. So taking that out doesn't affect anything. Okay, so what I'm saying is, let's cancel those out, okay? All right, so if we cancel that out, what does that make our limit then? The limit as x approaches 2 of 1 over just x plus 2, doesn't it? The top has canceled all the way out, so it's what remains there is 1 over x plus 2. I've changed my appearance, if you will, of this limit to this. But now, what can we do? Now we can substitute, can't we? It's no longer 0 over 0. So that's what this factoring does for us here in this case. It gets it to where I can plug that in. Ta-da. Okay? Now, if you remember back to when we first started talking about limits, this was a limit, that was the very first limit we started with. That limit, we did it with the table, and remember what we got? 0.25? Yeah, so this kind of bears that out or confirms that. This is a much more precise way of doing limits, so this kind of verifies it. Tables can be misleading somewhat. This, in that particular case, it wasn't. But anyway, we confirmed our suspicions back when we started this one with the table, so just wanted you to note that. Okay. All right, how about this one? What about the limit as x approaches 5 of x squared minus 5x over x cubed minus 125? All right. Well, guess what? We plug in the 5, what do we got? 0 over 0. Yeah, that's going to come up a lot. You can always check it, but more often than not on our problems, that's what's going to happen. We're going to get 0 over 0, which is an indeterminate form. You can't divide by 0. So we have to look at it. Now, so the only thing we know right now is factoring. Can we factor here? I do believe so. The top, we'll run into the common factor, so we got a common factor of x, pull that out. And then on the bottom, the bottom one may be one they don't cover a whole lot in algebra courses, but what have we got on, anybody help me there? What have we got on the denominator there? X cubed minus 125. We've got a difference of cubes, right? Well, it turns out a difference of cubes, and these are located in the book. There's the reference page in the back. The first reference page in the back has these factorings, difference of cubes. But it turns out if you got a difference of cubes, x cubed minus y cubed, that factors as x minus y times x squared plus x times y plus y squared. So if you're not familiar with that, that's the way you do it. A sum of cubes is similar, just to note, if they run into that. Sum of cubes, you have x cubed plus y cubed. It's x plus y times x squared minus x times y plus y squared. So it's similar, the minus sign's in a different spot there. But anyway, those two, if you run into those two types of polynomials, those do factor. Now in this case, I've got x cubed minus 125, and 5 is a cube, isn't it? 125 is 5 cubed. 125 is 5 cubed. So here, in this case, yeah, I've got this, and what's my x and what's my y? Well, the x is x, and then the y, it's 5 cubed, so y is 5, right? In this particular case, y would be 5, because that's 5 cubed. Yeah, so it'd be x minus 5 times x squared, okay, so x is x squared, plus x times y, so that'd be 5x, plus y squared, well the y is 5, so it'd be 5 squared, which is 25. Okay? All right. So that one does factor. Well, good news, just like on the previous example there, do a little canceling, can't we? Our x minus 5's cancel, so that leaves us the limit as x approaches 5 now of just x over x squared plus 5x plus 25. Aha! We're in business, are we? Because now, if I substitute, the denominator is not 0, right? So substitute in, you got 5, then you got 5 squared, that's 25, Plus 5 times 5, that's 25. Plus 25, 325. That's 5 over 75, which is, reduces, be 1 over 15. How's that? Okay? All right. Here's the next one. Any question, concern? All right, what about this one? What about the limit as h approaches 0? 4 plus h squared minus 16. So 4 plus h parentheses squared. Minus 16 over h. Well, okay, guess what? If I plug in h to be 0, 0 over 0. Specifically, denominator 0. But 0, 0 technically. Yeah. I guess if you wanted to, if you're really into factoring, you might say, hey, I can factor that. But let me show you this other possibility too. A lot of times when you run into something like this where you got parentheses, you got a binomial or something, a lot of times you just multiply that out or simplify it out. You know what I'm saying? Go ahead and multiply out the 4 plus h squared. In other words, FOIL that out. So 4 plus h squared, just go ahead and FOIL that out. It's 4 plus h times 4 plus h. So you got 16 plus 4h plus 4h plus h squared. Just don't square that, That's because it's FOIL, actually. So it's 16 plus 8h plus h squared. Yeah, just go ahead and multiply the 4 plus h squared out. You got 16 plus 8h plus h squared is what you get for that. Okay? All right, then. Now don't forget your minus 16, but that's important. And then divide by h. So those, nothing simplifies there on those. But what happens with the minus 16? Well, it goes rather nicely with the positive 16 up here in front. And 16 minus 16, that's 0. Those go out, don't they? And we're just left with 8h plus h squared divided by h. Now what? Still 0, 0, isn't it? But now what? What can we do? That's probably a little more recognizable. There's a little factoring there, right? I can factor that top without an h. The 8h times 8 plus h in parentheses. Divide that by h. H's cancel. And we're left with the limit as h goes to 0 of 8 plus h. Hey, that's good now. I can plug in the h to be 0. Okay, so sometimes simplifying either the numerator or the denominator. Just simplifying it. I mean, we didn't have any before where that worked, but yeah, if you can simplify, multiply things out and so forth, sometimes that helps and things work out. Okay, what about this one? Limit as x approaches a, x squared, the top's going to be x squared minus 3x plus 2 minus, and then parentheses around these, a squared minus 3a plus 2. And then that's divided by x minus a. Yeah, this is kind of a limited general because I'm not specifying what the A is. But it's the same idea. I want to get it where I can plug in x to be A. But guess what? Plug in x to be A, what happens? 0 over 0. That's usually on these, that's what's going to happen. Every once in a while they'll sneak one in where you just substitute, but yeah, it doesn't happen very often. So we have to do a little bit. Now, in this particular case, any ideas? Well, a little simplifying. What if I go ahead and distribute that minus sign there? Get the limit as x approaches A. So that'll be x squared minus 3x plus 2. That won't change, but then this will be minus a squared plus 3a minus 2 over x minus a. And a lot of times when you do that, there's a lot of stuff that cancels. Here, just one thing cancels, but it does cancel, right? 2 minus 2, those go out. All right. That leaves me then, limit as x approaches a, x squared minus 3x minus a squared plus 3a over x minus a. Okay, so after doing the canceling, we're still left with 0 over 0. But good news now is, hopefully, maybe you're not that familiar with it, but let's think about factoring here at the top. I've got 4 terms. And usually when you have 4 terms, one thing you want to look for is grouping. Group the first 2, group the last 2. The problem with this is they're not exactly grouped right, because here's what I want. If I factor off the, look at the first 2, look at the last 2. If I factor off common factor amongst those groups, let me write over here because this isn't going to work, because I get x, it'd be x times x minus 3. There's a common factor of x amongst those 2, right? And there's a common factor of a here. But for this to work, this and this need to be the same. So I've got to rearrange them because those aren't the same. So here's the way, and I don't know that this one exactly like this comes up. Usually, a lot of times you just group them like that and they're okay. But this one we do have to regroup a little bit. X squared minus a squared minus 3x plus 3a. So regroup them, make it the minus a squared with the x squared. Okay, with me there? Now if you group these 2 and these 2, here's what we get. You get the limit as x approaches a. That's a difference of squares. So I can factor it as x minus a, x plus a. Right? These 2, I can pull off a 3, but let me show you I need a negative 3. Here's why. So let's pull off a negative 3, it'll make it x minus a. The reason I need a negative 3 is because now this does match that. So I can pull that off. Go this way. Okay, so I pull that out. So I have limit as x approaches a. So I pull off an x minus a. I'm kind of pulling this out here. Pull the x minus a. What does that leave? X plus a minus 3. Is that okay? Question about any of it? It's okay? Okay. All right, now, look what we can do. X minus a, common factor, cancels out. So I wind up with the limit as x approaches a of x plus a minus 3. That's all that's left. I don't have 0 over 0 anymore, do I? What do I have? Well, it's x approaches a, so I replace the x, wherever I have an x, I replace it by a. It's there. You got a plus a minus 3, 2a plus 3, combine the left one. 2a minus 3. Yeah. So, just to point out here, yeah, like I said, this one, the other ones, you know, we came up with an actual number here, but this, because it was x going to just a in general, we're left with an expression in terms of a. So that's okay. I mean, that's what the answer is, 2a minus 3. All right?